Good afternoon, everyone, and welcome to today's SimScale webinar on CFD for forced convection simulation in electronics enclosures. My name is David. I'm CEO and co-founder of SimScale, and for the next 20 minutes or so, we'll take a look at exactly this topic. Right? It's already shown here on the cover slide here, and we're going to dive into that in a second. Before we do that, a couple of technical notes. We're using GoToWebinar to stream this session today, and it allows you to ask questions at any point in time during the meeting. You just, whenever something pops up that you'd be interested in, just put it in there. I can see those questions and try to address them later in the session. Because we know we have customers, all over the globe, and so this might be not a great time for everybody. So we will send this recording directly afterwards to everybody that's registered as well. So if there's some session or some part of the session that you haven't quite understood yet, don't worry, you'll get a recording right afterwards. All right, without further ado, let's dig into this. Few words before why this session, why do we cover electronics cooling simulations in this webinar today. And I think there's an interesting development underway. We're seeing lots of customers, lots of prospects being interested in that kind of simulation. And I think the big reason for that is that in every type of product, semiconductors, power electronics, some sort of sensors is being put in, all of them create heat. And a product that might not have had thermal management as a thermal management requirements 10 years ago or even 5 years ago might have it today, right? So we see the technical challenges we're going to discuss in the next 20 minutes in a lot of different industries, right? It starts with in oil and gas, we're seeing it in consumer devices, we're seeing it in transportation companies. So it's really across the board. There's so much thermal management going on. And that's why we think it's a very timely topic. And lots of customers have asked for it and lots of prospects. And so hence this session. And the reason why simulation plays a role, right, is exactly this. All of this heat that's being generated in those devices and those products needs to be managed. If us as engineers, if we are not doing a great job at managing this heat, this is the result, right? That's where simulation comes into play, right? And this is sort of a little schematic view that I use at times to sort of, I guess, explain why you should care about simulation, why engineers and designers benefit of simulation, right? At the top, we can see thermal management, thermal design being done traditionally, where you solely rely on physical testing, where you can just do so many iterations because eventually you're going to have to ship a product. And so this is where simulation comes into play, where you basically can turn the physical prototyping, the physical testing into virtual testing, and you can do more prototypes, you can do them faster, you can do them even in parallel and explore different designs faster, and ultimately it allows you to ship a better product faster to market, and that's money in your pocket, right? That makes your organization more competitive in a marketplace, and that's why we care about. That's the ultimate benefit here. Why another, and with that we're wrapping up sort of this little intro, why should I care about CFD in the cloud? Why should I care about SimScale? And the reason why we are around is the founding premise or the founding idea behind SimScale was to get rid of the traditional barriers that come with traditional simulation tools. And those are specifically all the high-performance computing hardware you need to support a seed of simulation software. It's about costs that occur from hardware, but also costs that occur from software licenses that oftentimes comes with a lot of CapEx, not OpEx, so it doesn't allow you to variably and flexibly scale up and down, but you actually lock in budget for hardware, you lock in budget for software, and you pay for what you have, not for what you need. Last but not least, because it's expensive, because it's a big investment for an engineering organization, typically it's only done if somebody uses it all day long, right? And hence, traditional simulation software has been built for experts to use. And I guess that's the mission we have at SimScale, to sort of remove these barriers and ultimately make simulation much more accessible to a wider audience. And doing that very brief here, the two first things, I know that among today in the audience there's many existing users, but also several new users, people not familiar with SimScale. So the first two ones we're going to see in a second in action, right? It's zero software, zero hardware footprint. So it's a web application. There's no install, there's no hardware rollout. Everything you need is a web browser. The second piece is that you have the flexibility with SimScale to actually start for free on our public community plan. Once you want to do professional work, proprietary work with SimScale, the financial upfront commitment is much lower than compared to other solutions, and then you basically buy on-demand computing power on SimScale, which allows you to deal with your simulation demand much more in a much more flexible way. Last but not least, we pride ourselves with the great support, with the capability of actually sharing in real time a simulation project with our staff, with your colleagues, with clients, and so there's a lot we've done to make it to make our users faster, successful than with traditional software. All right, but that maybe just as a super short introduction to why we're here today. For the rest of this session, we're going to talk about, we want to see this in action, right? How can SimScale, how can cloud-based CFD help us as engineers, as designers, deal with thermal management problems more effectively, faster, right? And the example we're going to look at today, and you're going to see it in action in a second, so I'm going to jump from the slides away and going to show you the product itself. This is the example we look at today, and it's somewhat close to applications we're seeing on a regular basis from customers, where, and arguably it's an extreme case, right? This is a high power density enclosure where I think it's about 100 watts. I'm going to look at it in a second. 100 watts of power is in here, right? We have a bunch of electronic components. So we have the CPU in brownish red down here. We've got transformers, chips, distributed over a couple of boards. So a lot in that package here. And today what we want to specifically look at is the cooling strategy of forced convection, right? So you see it already here in the lower left. These are fan inlets. So we're going to mount some fans here, not modeled here. So we're going to apply them as boundary conditions. And on the right, here's outlets. So we want to have forced convection cooling within this enclosure. We've got customers across the board, right, that are simulating natural convection, so naturally cooled electronics enclosures. There's sometimes liquid cooling, etc. So all of this is something we address, but today we want to focus on forced convective cooling. So we're using air to transport the heat away from these components. This is the rough setup. This system is operating under normal room conditions. So we're looking at an inlet temperature of 20 degrees Celsius, open outlet, sort of the scenario. And again, just why this geometry, right? For us, this is representative to a lot we're seeing in various industries. Quickly on the sort of the challenge at hand, there we go. Around 100 watt in total power within this enclosure. Cabinet volume, small, and that sort of is the power density if you compare it to the base plate. So very high, right? Specifically, folks involved in data center design often look at this metric, right? And now looking at this, we are asked to validate whether or not the cooling strategy we designed or engineered here is actually sufficient to operate all of these electronics components in a under safe temperature, right? Even at peak load, peak load of all of the semiconductors in here. And so typical design parameters we're seeing customers looking at is, first and foremost, heatsink selection here on the CPU, right? It's something that's present, very, very often. Also material selection of the heatsink, etc. So that's one thing, and we're going to look at it today. The second thing is fan selection. Again, there's a price component to it, right? There's a noise component to it. There's how many of them you want, etc. And then obviously where to put them, fan placement, and last but not least, how to arrange the components within the enclosure to make sure I'm making maximum use of the air I'm flowing through here. since this is supposed to take only 20 minutes today, and warning, it might take longer, a couple of minutes. I'm sorry for that. But we cannot look at all of this, right? So we'll just look at two scenarios. One is we're going to look at two different heat sinks, and the second piece is we're going to look at different fans that we put in here and see the effect. And the purpose is really to see very hands-on how SimScale helps to make these design decisions earlier, faster, and ultimately help to reach a good product faster in time. And so that was a lot of slides and theory, and I think we're all here to also take a look at the actual product. So let me quickly jump over here to the actual product. All right, so in case you do not yet have a SimScale account, you can just browse to simskill.com in the top right. I mean, I'm already logged in, right? But if you're not logged in, you can just create an account. It takes you 30 seconds, then you're in there, and you don't need to to trust what I'm telling today. You can just experience it yourself and test it on your own designs, right? Once you're in, this is how it roughly looks like. This is my dashboard, and what I'm going to do now is I'm opening up a half-prepared project. So we don't want to wait for the mesh generation today and for the simulation runtime. So I'll have something prepared, but I want to give you a feeling for, at least a feeling for how it is to use SimScale. So what we would do in such a scenario is I might have designed my my enclosure. I might do my design work in a desktop CAD system, in a cloud-based CAD system. It actually does matter. I can bring in from various third-party tools CAD files into SimScale, and this is how it looks like. So I want to upload a new geometry. Let's assume I designed this geometry in a local CAD system, so I upload it, and this is now automatically stored within the SimScale project. And I can access it from multiple devices. I can use mobile devices. I can use different computers. My colleagues can look at it. And yeah, the beauty of the cloud, I guess. All right, you can see already it's loading. Colors missing yet. They should be there in a second as well. There we go. So this is the board we looked at, right? And again, it looks and feels like a desktop application, right? I can interact with it. There's no lag times. It's client-side rendering. And so what I can do now is let's quickly hide this, right? And this is exactly the board we looked at, right? And so for the existing users of SimScale, what I quickly want to demo is a new feature we just recently launched for these types of application, and this is the automatic creation of the flow volume, right? And so let me quickly bring that back, because you can see is that this is the actual enclosure and this is the actual geometry of the boards in there, right? And in order to carry out now the flow simulation in SimScale, what we need is the flow domain, so the air domain in here as an actual CAD part, right? And in the past, you needed to do that locally or in your CAD system, and I will support that on SimScale. And so it works like that. I want to create an open inner region, and I want to keep the existing parts. And I say, okay, and now I pick the faces. I pick a bounding face here and a bounding face there. So literally the faces that sort of show where the flow volume shall end, right? So primarily inlets and outlets, and then just one seat face in here. And I hit the start button. And this takes now a few seconds, and I'm going to get that back. To not wait for this, let me quickly jump over here, and this is exactly, I quickly prepared that before the session. This is then exactly how it looks like, right? So let's quickly hide the enclosure, and you can see that the flow volume was created as an actual part, and all of the Boolean work to be done and imprinting work, etc., to make sure contacts are nicely matching between flow and solid regions is done automatically, right? So you can see that you can see now the other one is also done. Just quickly jumping over here again. See, this is how it looks like. This is how it works, right? So it adds a lot of convenience here. All right, Next step, what I would typically do is kick off the mesh generation. Quickly, I've done that before as well. And there's different meshing algorithms on SimScale. This now was generated on a 32-core machine. And let's quickly take a look. So we're looking at around about 10 million cells, right, for this guy. And also, again, I can see that the features are automatically refined. The feature edges here. Let's hide the enclosure. And this is the flow volume we're looking at, right? And let's quickly take a look at the components as well. Hiding the flow region. Here's the components, right? All of them meshed as well. And again, like, I can see that features have been refined and respected. And none of this was, I mean, I could now go in there and say, okay, hey, I have a specific region of interest that I would like to take a closer look at, or I don't know, I might not like the big cells here, so I could now add local refinements, but in a first step, there's no need to do that, right? All right, let's spend another sort of 2 to 3 minutes on just getting a rough idea of now how the simulation setup is done on SimScale. The goal for the session today is not to discuss the details of turbulence theory and related concepts, but really for you to get an idea whether or not this would be a valuable tool in your engineering work. So what I'll do is I'll create a new simulation. I'll select conjugate heat transfer, click OK, and a new simulation has been created. I go back and I want and I assign a geometry that I want to simulate. And now I can, based on this, set up the simulation. We won't do it again entirely. I'm going to show you the results in a second, but just for you to have a feeling, right? And the most important concepts, the 3 most important concepts is A, materials, right? So I want to assign air to the air region. I want to assign solid materials to the air, to the solid parts. So in that case, I would assign air to the flow region. So that's good. And then I would assign, let's assume that's an aluminum enclosure. I assign it here. You get the idea, right? And I would go through the components and boards and assign specific materials, and automatically I would have the right conductivity of these materials, so that's taken care of. So I'll stop it here just in the interest of time. The other important piece would be boundary conditions, and here also I would assign, velocity inlet boundary conditions. Or I could also choose fan boundary conditions, but let's say, okay, I'm having here, make that very simple. We're blowing in at 50 meters per second at 20 degrees Celsius or 293 Kelvin. So that would be my inlet. And then over here, I do a pressure outlet. I think you get the idea, right? None of this is very similar to other applications in that realm. Gauge pressure 0, so I'm looking at an external normal pressure, and that's that. I could now, also assign convective boundary conditions for this, for the enclosure externally, etc. That's all possible. But in the interest of time, let's also pause it here, move one step further. Last important concept is power sources. And for that, let me quickly hide the enclosure. Let me hide the flow region. And let's quickly see what I actually said. What is the wattage of the CPU? Let me quickly go back. So we said our CPU would have 40 watts, right? All right. So how I would do that is I would assign a power source and say, all right, we've got 40 watts over here. 40 watts. This is the part, like, CPU. There we go, right? And this would now this would be the same concept I would apply for the other components in this enclosure, and I could apply the specific wattage there, right? And yeah, maybe as a last step, I can then choose, on how many cores I want to run this, and because 10 million cells, I'd probably go with a 32 or a 64 core machine. We could probably even take advantage of a 96 core machine. So this case is big enough to actually take advantage of these big computers, and yeah, we'll kick it off, right? In the interest of time, we haven't gone through that in its detail, but I want to make sure you've seen once the entire workflow. So let me quickly hop over to this project. And again, this is slightly different. The internals are the same. I've modeled the outer space a bit different, but other than that, it's very similar, right? We have the fan inlet, we have the open outlet, we have the power sources over here. So small chips, CPU defined. We have the materials defined, right? So there's not more to it. And then you kick things off. And now we're gonna take a look at the solution fields. What I didn't define earlier is what we're specifically interested in is a maximum temperature, right? Which components reach maximum temperature, and specifically the CPU temperature, right? Because this is our most important chip in here. This is the with the highest wattage. So we want to make sure that we have the average temperature of the chip under control, of the CPU under control. And so what you can also do is assign, we call it result control items. So where you say, okay, I want to specifically monitor the average temperature or the peak temperature of a component, right? And that's also what I've defined in that simulation. All right, once the simulation is carried out, you can open the solution fields up here. And now, again, this is something you might have all seen in other softwares. The beauty of this is it runs completely cloud-based, right? So we can now visualize results. So let's start off by saying, okay, I actually want to see a temperature plot here, right? So I turn on the temperature view, and I get directly sort of a solved case of this is 323 Kelvin. So we're looking at 50 degrees Celsius red, right? So the immediate thing that gets clear is that, okay, I have those two components here that get very hot, a component over here on the right, and it gets very hot, and it might be something I want to look at, right? And I can now interact with it. Let's hide the CPU. Hiding that, and also like that, this is something you've all seen, right? So you can now click here and say, okay, we're looking at just about 50 degrees Celsius, right? So roughly 48. And I can now go in here and say, what do we have here? Oh yeah, that's even north of 50 degrees Celsius, right? So again, probing and looking at what I can see here, right? And looking whether or not this works. Another thing, let's turn on the a cutting plane showing velocity, right? So this is now a plot through through the middle of the enclosure, and that highlights and that shows velocity here, right? And I think one thing to note, I think what we can see is, I think an unexpected factor here is that I have nearly no airflow going here at the bottom of the enclosure, right? That might be an interesting finding here. The heatsink seems to block a lot of the airflow, so I can analyze that as well, right? And I could now go into detail, look at streamlines, look at isosurfaces, isovolume plots, etc. So the usual tools that that you would expect from an engineering simulation software. Now you've seen once from basically get a rough impression of what it means to run such a simulation on SimScale. So to drive the point home, or to sort of conclude this webinar, let's jump back to the slides and see what we as engineers would now do with this information, right? We talked about this. Oh, sorry. This is just what we've seen, right? These are literally captured screen snaps, right, from what we just looked at, right? So I can analyze all of these fields, and I can get this information without any testing just by using a web browser. So no hardware, no dedicated software that sits somewhere, and just a web application where you can run high fidelity analysis of this kind. And what would we do with it? I think a big takeaway here is, okay, the CPU is scratching 50 degrees Celsius, right? So we want to might want to take a look at how to reduce this. And as you can imagine, as discussed earlier, we're going to take a look at a quick iteration on heatsink selection. On the left, you can see the plate fin that we just visualized, that we just analyzed. On the right, in my CAD system, I quickly swapped the heatsink. You can see now it's a pin fin, and I go about this the exact same way, right? I would bring this geometry into the same project in SimScale, just reapply the simulation setup to this new geometry and run it again, right? And that's what was done here. And what you can immediately notice is that the heatsink already is significantly cooler, right? We can see it, the pin fins are rather on the yellow, in the yellow realm. The plate fin is hot. Confirming that with the top view. And I think the important piece is all the other components, as we would expect, are not really affected. We can see that the flow field might be affected around the pin fin heatsink to also have an effect on the components around it. But overall, the massive impact is on the CPU. Again, here the velocity plot, also what we would expect. I can see a different flow field around the heatsink. This is a glyph plot, right? You can see the little arrows indicating the direction of the airflow. And putting this together sort of as a first small design study, within minutes I swap this design, I quickly kick things off again in the cloud. I have the heavy lifting done in the cloud. I can run a high fidelity 10 million cell CFD simulation from a normal laptop, from a Chromebook if you will, and have these insights that with this different heatsink, I get a significant reduction in peak temperature of my CPU. Here, 16%. So the pin fin seems to be much better in that scenario. And to drive this point home, again, iterating with SimScale, another one is literally fan selection, right? In that case, we've made it very simple. We just said, okay, if I bring in stronger or maybe a weaker fan, what would be the effect? And the beauty here is that it's even the same geometry, right? It's the same geometry. So changing the fan curve or changing the fan bounding condition is a couple of clicks, and you can run these simulations entirely in parallel. And also here, we can immediately see, okay, in this scenario, the 10 meters per second is definitely not acceptable, right? Multiple components reach the 50 degrees Celsius that we're trying to not cross. I have more components reaching that. The CPU gets hotter, etc. Again, we can just quantify what this would mean, right? Same view here. On the right, you can see lots of bigger portions of the board reach peak temperature, not acceptable. And again, it depends now on the specific scenario, right, and on the constraints of my design project, whether or not I want to go with a stronger fan that gives me more, I guess, safety to operate my enclosure or my system. Again, it's just like a visualization of what you can do and how you can quickly iterate through these decisions. Putting this together, I might come to the conclusion that my peak temperature is not significantly smaller, right? So that a bigger fan or a stronger fan might not be worth it. And I have this confidence in my design decisions thanks to just a quick simulation in the cloud using SimScale. And with only 8 minutes in overtime, let's wrap this up. I think what we've seen over the last 25 minutes is how we brought in a typical enclosure from my local CAD system, brought it into SimScale. This is what we've seen in the top left, right? What we've done is we created a flow volume extraction. So we've done some pre-processing steps inside SimScale, created an automatic mesh. We assigned materials, we assigned boundary conditions, we assigned heat sources, and then we kicked things off in the cloud. I mean, we didn't, right? But we could have. We looked at finished results, and then we post-processed and visualized these results also completely in the same application inside the browser, right? Again, if you look at these screenshots closely, all of this is a browser, and there's zero software, zero hardware installed. And with that, I would encourage you to, if that sounded interesting, if you're intrigued by giving this a spin, I would encourage you, simskill.com, create an account. It's free. You can just look at it yourself. There's tens of thousands of public projects where other engineers, other designers have been using SimScale to simulate similar applications. You can take a look at that. You can engage with our application engineering staff to discuss your application. So I'd encourage you to take a look. Testing, because there's no install, because there's no download, it's so easy to test. So I encourage you to, would be great to see you around on simskill.com. With that, I would officially close the session today, and thank you so much, and I hope to see you on simskill.com. Take care, bye-bye.